Hey team video, we are talking about notes 41 today. So we're talking about something called the fundamental theorem of algebra. Doesn't mean that this is the first thing you learn, it just means this is a super important thing. So the thing that we're going to do is identify how many roots a polynomial has. So the fundamental theorem of algebra states that all polynomials have some kind of solutions. Remember that the other word that we typically use to describe this is roots. It also says, and this is where we're going to focus today, the degree of the function states how many roots a graph has, even if they're imaginary. So we'll get to the imaginary parts in a second. Let's just look at the basic meaning. So what we see here is a graph, and we can see that the equation is here, and then we can turn that into the factored form there. Provided both of those for us so we could take a look at what they were. So using this information right here, we can see that the equation has an x squared as its highest degree. This is what we call the degree of the function. What that means is that if the highest degree is 2, the biggest exponent is 2, that means that there are 2 roots. If we look at the graph, we can see here's one root and another root. So that's pretty awesome, and that's all that the fundamental theorem says. From there, we can look and we can say, okay, our theorem, or our roots are at certain places based on where they fall on the graph. So we can see we have -1, -2, -3, -4, -5, and then we have 1, 2, 3. All right, we could also tell that from the factored form here. We know we could switch the sign to get -5, switch the sign to get 3. So we'd say that the roots are at -5 and 3, and we don't need this section over here. So we know that this is x squared, right? We see that in the graph. It gives us 2 roots, and we see where those roots are. So fairly simple. Let's look at it with a cubic. So with a cubic, we see this graph that looks like this. We know it's a cubic. We see in the equation that the largest exponent is 3, so there should be 3 roots. So I can count on the graph 1, 2, 3 roots. We also know the factored form is here, and we can switch those signs to say -1, +2, +3. See that on the graph at -1, +2, and +3. So I know the roots are at -1, +2, +3. Pretty cool for a cubic. Let's see if it works for a quartic. It is the fundamental theorem of algebra, so hopefully it does. Here we see a negative quartic. We see x to the 4th is the biggest exponent, so there should be 4 roots. And then we can see the roots from the factored form, -2, -1, +1, and +2. We see them on the graph, -2, -1, +1, +2. So we can see those there. We can write them right here where the roots are. So basically what we're saying here is the degree, which is the highest exponent, right? The highest exponent tells us how many solutions or roots a function has, which I should see on the graph. Sometimes we know that we don't necessarily see them though. So let's check out these ones here. So it says, but what about these? So we see the x-axis here, and we see that there's only one solution here. So they tell us the equation though is x to the 3rd, so there should be 3 roots, but I only see one of them. I also see the factored form here. I know one of those roots is at -3, right? And we see that on the graph here, -1, -2, -3 right here. That's pretty easy to tell. And then we see this. This is what we call an irreducible quadratic. If I could spell that, irreducible. So there is a real root at -3, but there should be 3 total roots. So there is what we call imaginary roots, and there's 2 of them. All right, so we have to, according to the fundamental theorem of algebra, there has to be 3 roots. And only one of them is real, right? That's the only one that we can see on the graph. So that means that there must be 2 imaginary ones. All right. So let's check out what that means for something like a quadratic. So quadratic is here. We see that it never touches the x-axis. So we see x squared, there should be 2 roots, but I see 0 of them. So we know from this, like if I tried to factor this right now, the 2 goes on top and the 2 goes on bottom. I need something that multiplies to get to and adds to get to. There's nothing that goes there, right? That's because this is a irreducible quadratic, just like above. And so I'd say there are no real roots. I can see that there's nowhere where it touches the line there, but there should be 2 roots. And so I know that there has to be 2 imaginary roots. Imaginary roots come in pairs. Remember when we had the positive and the negative version, like 4 plus 2i? We always had them in pairs. So you should always have 2 imaginary, 4 imaginary, 6 imaginary. But in this case, we have 0 real roots, and we have 2 imaginary solutions, so that we can get that x squared. Alright. There's one more thing that we might see, which is called multiplicity. Multiplicity deals with double roots, and we've dealt with these before. We've talked about them a little bit. But double roots is what happens when the graph bounces, right? So it can bounce off the bottom or off the top. But we see this cubic crosses through, comes down, bounces off the x-axis, and goes right back up. Right? So we know that there should be, according to the fundamental theorem of algebra, there should be 3 roots, but I only see one of them. Again, I see this one right here, and I only see one of them. There's also one here, so actually, instead of saying that I see one, I'm actually going to say that I see 2. I see 2 of them. I see one that bounces. That one actually counts double. So this is what we would call a double root right here. I can see that in my factored form by looking for a place where the factor is written 2 times. So I see x minus 2 is written twice. That's going to be this one at positive 2. Or I sometimes see it written with this squared notation. That means that there are 2 of those. That's how we see a double root in the equation. So there's a root at negative 2, right? And there's a double root at positive 2, that place where it bounces. Let's see if we can find another one. So here on this one, I see that there is a solution there, a solution here, and a double root here. I know that that's a double root because it doesn't pass through, it bounces. So according to the fundamental theorem, there should be 4, but I only see 1, 2, 3, right? That means that there is a double root. I know that it's right here. And I see that the double root exists at this location here. I know that it could also be written this way. So I know that there is a double root at positive 2. There are also individual roots at 0 and at positive 1. So I know that there are real roots at 1 and 2 and a double root at 3. This doesn't have any imaginary solutions because it has 1, 2, 3, and 4 solutions counted for. In the top one, we had 1, 2, and 3 solutions counted for, so we had all 3 that we needed. Right? So as you look at your assignment 40, what you're going to do is you're going to graph the functions on your calculator. Right? So first things first, take this, type it in your calculator. You're going to draw a quick sketch of the graph that you see. So I see that this is x to the third. I'm guessing, I haven't looked at my calculator yet, but I'm guessing this looks something like this because it's positive x to the third. I know the degree is 3. Right, so let's say my graph actually looks like this. My real roots are going to be here, here, and here, anywhere that touches the x-axis. So I would say that there are 3 reals, and they hit at 1, 2, 3, 4, 5, negative 5, maybe 2, maybe positive 5. Right? I would say that there are 0 imaginary solutions, and I would say that there are 0 double solutions. Right? Let's say for some reason my graph looked more like this. Right? My degree is still 3. I have 1 root right here, so that's negative 1, 2, 3, 4, negative 4. And then I would say that there are two imaginary solutions. I don't know what they are because I haven't done any like really hard math. But this part here, I know that that's not touching the x-axis. So I know that there are two imaginary roots. And then there are 0 double roots. Right, so you're just going to go through, find the real roots, find the imaginary roots if there are any, and then find the double roots. That's all for today. Thanks.